Okay, good afternoon all. And so today we are going to discuss about X-ray diffraction and reciprocal lattice. Okay, so basically I will try to cover these two topics in today's lecture. So okay, so let us see what is X-ray diffraction. But if we will learn in details about this X-ray diffraction topic. So one of the topics in Unit 1 is also this Debye-Skerrer method. So this Debye-Skerrer method we'll learn in detail in a later class. But today we are basically going to learn about the basics of X-ray diffraction technique. And then another interesting concept which is known as reciprocal lattice. Okay. Okay, I hope this PowerPoint is in full screen now. So the topic is X-ray diffraction and reciprocal lattice. Okay, so these two are different topics. X-ray diffraction is just one topic, and reciprocal lattice is another topic. If we go as per your syllabus, then two more topics are there, after which immediately follows X-ray diffraction, and those two topics are atomic scattering factor and geometrical scattering factor. But in order to understand those topics also, we need to have some knowledge on reciprocal lattice. Okay. Therefore, first let us learn the reciprocal lattice method, and then we can we can learn about atomic scattering factor and geometrical scattering factor methods. Okay. Okay, so so you can see in the background of this slide, you can see an instrument. So this instrument is basically X-ray diffractometer. So you can see here the name is written. So Rigaku X-ray diffractometer. So Rigaku is a company which builds such X-ray diffraction equipments. Okay. So and here in this there is a monitor here, desktop monitor. In this desktop monitor, you can actually see some peaks. Okay, several peaks you are able to see. So these peaks actually corresponds to various crystallographic planes of a given solid sample or a given crystalline material. Okay, so each of these peaks. Okay, so when we will be learning about Debye-Skerrer method, so there we will learn how these peaks or various peak positions are actually determined. So there we will learn, because corresponding to each substance or each crystalline material, we will get such characteristic peaks. Okay, these peaks you can see here on this monitor. So how this happens, we will discuss in great detail. So when we will be learning about Debye-Skerrer method. So yeah, that is basically I wanted to tell you. This is the X-ray diffractometer method. So this is the diffractometer. So here inside the chamber, the sample is placed, and a monochromatic beam of X-rays is illuminated on the sample. Okay, and when this sample interacts with various planes of a given crystalline material, so we get the diffraction patterns, and the diffraction patterns are characterized by peaks. Okay, corresponding to each lattice plane. Okay. So the first topic is X-ray diffraction. So yeah, this is actually the same instrument which I was just talking about. So this is the diffractometer. So inside here, the sample is placed, and then there is some software. Okay, the software which controls this instrument, and also this with the help of the software, the measurements are done. Okay, once the measurements are done, so this results, the peaks which I have just mentioned, they correspond to the various planes. Okay, what are these planes? These are the Miller indices. Suppose 100 plane, 111 plane, or 211 plane, 121 plane. So such planes can be identified from the peaks as you can see here. And when this data is generally compared to some standard data, okay, standard data which is available worldwide, internationally, and with the, if you compare your own data, whatever data you are getting here with the standard data of materials, then you can actually identify which material you are studying. Okay, Suppose I give you some solid material, solid substance, or some crystallographic, some crystalline material, okay, or some unknown solid, okay. So you don't know what that is. So I know I give it to you and I ask you. So find out this material and let me know or report to me in next 2 days maybe. Then one of the methods what you do to identify the crystalline material or the substance is you do this X-ray diffractometer or X-ray diffraction experiment in this diffractometer setup. Okay, and the result which you will get, you will compare that with standard database, and then you can conclude that okay, the material is of this type or the material is having this crystalline structure. Okay, anyway, so let us learn the basics. So why X-ray diffraction is used. So so in order to learn more about the crystals, or in order to identify unknown crystalline materials, so what are the sources that we can generally use? The sources which you can generally use are X-rays, electrons, or neutrons. Okay, so why X-rays, electrons, and neutrons? To that point will be coming next, because you see why that these are so you may be asking, why cannot we use visible light? Okay, the problem is visible light has huge, very long wavelength, okay, which is of the order of 5000 angstrom. Okay, and what is the interplanar spacing or interatomic spacing in the crystals? The interatomic spacing of the crystalline materials is of the order of 1 angstrom. So you see, if you are using some source like visible light having 5000 angstrom of wavelength, to know about some material which has only 1 angstrom of interplanar spacing, so basically we will not get any information. Okay, so why that we will not get any information with visible light if we want to study these crystalline materials? Because the visible light will not be able to interact with the planes of a given crystalline material. Planes, okay, planes are, because the planes are like planes are interatomic spacings are so small, and this wavelength of visible light is so long that there would not be any interaction with the planes with the, and visible light. Okay, so suppose you illuminate any sample, okay, any material or any like anything like salt. Okay, salt is also a crystalline material. So most of the metals are also crystalline materials. So what information you can get? So uh, most of the lights will be getting reflected from the surface itself. Okay, because the light cannot exactly penetrate the material. Why? Because of this problem with the wavelength of light, because light wavelength for visible light is very long. So in order to compensate that problem, so we have to use those sources whose wavelengths are comparable to the interatomic spacing. So what are those sources whose wavelengths are comparable to interatomic spacings? Those may be X-rays, electrons, and neutrons. Okay. So let me go to the next point. The wavelength of incident waves should be of the order of interatomic spacing, which is 1 angstrom. Okay. So the incident wave means be it X-rays, be it electrons, be it neutrons. So the wavelength which we require to interact with the various crystallographic planes. Okay, that wavelength should be of the order of the interplanar or interatomic spacing. Okay, so interatomic spacing topic we discussed in the last class. So that spacing d value, okay, small d value, so that should be of the order of 1 angstrom. Okay, the wavelength of the incident radiation which we should use should be of the order of 1 angstrom, because interatomic spacing is also of this measurement, okay, of the order of 1 angstrom. Okay, so what happens we would see in a while. So in that case, the waves should be able to interact with the atoms of the solid. Okay, so when you are using a wavelength, using a source like X-rays, electrons, and neutrons, etc., in that case, the waves would be able to interact with the atoms in the solid. Okay, why? Because of their wavelengths, which is almost equal to interatomic spacing of 1 angstrom. Okay. So now the question is, we have three sources. Okay, we have mentioned mainly three sources, and all these three sources are capable of producing waves which has about 1 angstrom of wavelength. But then why we have to use X-rays? Okay, so then why we are not using so electrons or neutrons, but we are predominantly using X-rays? Okay, so a beam of electrons is scattered by atomic nuclei as well as atomic electrons. Okay, so this is a problem with of using electrons, because electrons are scattered by nucleus and also other electrons. So similarly, in neutron diffraction, okay, when you are using neutron as the source of your wave, so neutrons are scattered mainly also by the nuclei of the atoms. Okay. So in both these cases, we can see that whether it is X-rays or neutrons, we will see that they will be scattered by nuclei of the atoms. Okay, so then these are the two disadvantages of using electrons and neutrons. Then let us come to let us see what is the advantage of using X-rays. Okay. So on the other hand, 1 angstrom of X-rays, okay, 1 angstrom of wavelength, 1 angstrom wavelength of X-rays can be produced by an accelerating voltage of about 10 kilovolt. Okay, so generally the accelerating voltage, so when this X-ray diffractometer instruments are operated, so to be precise, 10 to 50 kilovolt of accelerating voltages are used to produce the X-rays. Okay, in that case, almost 1 angstrom of 1 angstrom wavelength of X-rays can be produced. Okay, so then the wavelengths produced by voltages of this range can produce observable diffraction effects with reasonable values of angle of diffraction and interplanar spacing. Okay, so this is one of the biggest advantages. So when you will use wavelengths, such wavelengths, I mean wavelengths which are of the order of 1 angstrom, okay, in length, so and which can be produced by this much voltage, around this much voltage, to be precise 10 to 50 kilovolts. So voltages, so wavelengths produced by this much voltages can produce observable diffraction effects with reasonable values of angle of diffraction and interplanar spacing. So what is the angle of diffraction? We will learn next probably. I will show you in a figure. So then we can observe a diffraction. Okay, so diffraction of this rays, diffraction after the X-rays are incident on various crystallographic planes. Okay, the figure I will show you. Okay, so another advantage of using X-rays is X-ray diffraction is a very widely used method, and it is cheap and convenient. Okay, so X-ray diffraction methods are generally cheap and convenient to use. So X-ray diffraction is widely used as compared to electron diffraction or neutron diffraction, whose setups and whose experimental arrangements are much more expensive and complex. Okay. So, okay, so a brief history about this X-ray. In the next slide, I'd like to discuss about this brief history of X-ray diffraction. So X-ray diffraction method to study crystal structure was first studied by these two people. So one is William Henry Bragg, and the other one is William Lawrence Bragg. So they are actually father and son duo. And interestingly, in the year 1915, so both were awarded Nobel Prize in Physics. Okay. So what was their work? Their work was basically to where that they found out the crystal structures of sodium chloride, zinc sulfide, and diamond. Okay, so for their pioneering work on determining the crystalline structures with the help of X-ray diffraction, so both of these persons were awarded Nobel Prize. Okay, then they pointed out out that lattice planes in a crystal behave to X-rays as lines in a diffraction grating. Okay, so in a diffraction grating, you must have studied our diffraction gratings in your undergraduate course. So in diffraction grating, we have some opaque space and then some transparent space, then opaque space, transparent space. Okay, so what they can do, those type of setups, they can produce diffraction grating. Okay, when some light, monochromatic light is incident on that arrangement. So in X-ray diffraction also we get the same result. Okay, because in this crystallographic planes also behave to X-rays as lines in a diffraction getting. Okay, so same analogy we can use. So this X-rays, when they are incident on various crystallographic planes, and then in the result we'll get some diffraction pattern. Okay, and this same diffraction pattern is studied to learn more about the crystallographic material or the crystalline state of the material which we are studying. Incident waves are reflected specularly from lattice planes. Okay, so incident waves are specularly means they are incident on the lattice planes and they are reflected off. Okay, those reflected rays actually form a diffraction pattern, which we in turn we study, or which in turn is the basic of this particular method of learning about crystalline structure of materials. So a crystal can be considered as a grating, and nature of diffracted beam is determined by the spacing small d. Okay. So a crystalline material is considered as a grating and X-rays as the source of light. And the nature of the diffracted beam, okay, so what result we get after the diffraction, that is also determined by the spacing d. D is the interplanar spacing, okay, or interatomic spacing. So these two people, they Bracks Law, very famous law. I hope also many of you know this Bracks condition or Bracks Law. So this is basically the equation n lambda is equal to 2d sine theta. So n stands for the order of diffraction, lambda stands for the wavelength of X-rays, D stands for the interplanar spacing, and theta is the this Bragg angle. Okay, so the angle. Okay, so this is the specular reflection. This incident ray is the ray or X-ray is incident on this crystal planes. Okay, so these are various crystal planes. Can I annotate here? Yeah, so these are various crystal planes. So 1, 2, 3. These are various crystal planes, and these X-rays are incident on this plane, making an angle theta with the planes. Okay, with each plane. Okay, so these are the planes are parallel. This plane is this plane, this plane. So they are parallel. Okay. So remember that this angle theta is made by the incident X-ray with the planes. Okay, not with the normal, but with the planes. Okay. So parallel planes. And this is the common line, and so these angles are equal to theta. Okay. So similarly, although not shown here, this angle will also be theta. Okay. Once the X-rays are incident on the plane, then they are reflected. Okay, reflected X-rays, as you can see here, reflected X-rays. So this is the normal somewhere. The normal is not shown here. So this angle and this angle would be equal. Okay. Similarly, this angle and this angle, the opposite angles would be equal. Okay. Okay. Yeah. So, and this is the very famous Braggs law. So this condition has to be satisfied to obtain a diffraction pattern with the X-rays. Okay. And lambda equal to 2d sin theta, and which is known as Braggs law. Okay. Okay. So I have to remove the annotation because yeah. Okay. So incident rays. So you see the figure, because now okay, undeviated X-rays means this X-ray, it does not experience any reflection, although it passes through the crystalline material. Okay, because it does not follow this Braggs law. Okay, okay. So let me go to the next slide. Can I go? Okay, so here, okay, so this much, so these two pictures you can see, this I have taken from your textbook, this Ajay Kumar Saxena textbook on solid state physics. Okay, so mostly I follow that book. And so this derivation of this Braggs law, this particular equation, which I just showed to you, again, let me start the annotation so that so so this derivation of this equation is done here. Okay, how we can derive Braggs law. So this Braggs law derivation is a very geometrical topic. Okay, so it's very mathematical or trigonometrical, rather it's a trigonometrical topic. So in order to do that, we have to see the figure, okay, that we had drawn, that I had shown you earlier, and that's directly followed from the Ajay Kumar Saxena textbook. Okay, the textbook is actually available in our department library also, which was set up recently, as you know, and also maybe some other textbooks are available in the university library. Okay. Okay, so let me show you the derivation. So figure 2.1 means, okay, let me stop this annotation again, and this is the figure 2.1, this, okay. So what is the path difference? Let us check. AB minus AD equal to n lambda. AB minus AD equal to n lambda. Okay. So you see, so when we get like interference, okay, interference condition. What is the interference condition? The path difference is equal to the equal to n lambda. Okay, path difference is integral multiple of the wavelength. Okay, so what is the path difference from this figure? Sorry, from this figure, it is basically AB minus AD. Okay, so because you see this ray of light has traveled AB, this ray of light has traveled AD, so AB minus AD equal to n lambda. Okay, and we have to separately calculate the values of AB and AD trigonometrically. Okay, trigonometrically from this given figure. Okay. Okay, so let me read what is here. So the figure shows a monochromatic beam of a parallel axis. I hope you know already what is a monochromatic beam. It has single wavelength. Okay, penetrating a stack of planes of spacing d in a crystal at glancing angle of incidence theta. Okay, so stacking plane means these three planes, as I have already shown you with annotations. So the angle which this in monochromatic X-ray max is angle theta. Okay, so each plane reflects a fraction of the incident beam energy specularly as if it is by a mirror. Okay, so this is these rays of X-rays are reflected from each of these planes in a way it would seem to us that they are reflected like a plane mirror. Okay, because these are this various planes. Okay, these are the various planes which compose a crystalline material. Okay, so lattice planes or crystal planes you can call them. Okay, So they are assumed to be like flat as a plane mirror. Okay, and you can see the type of reflection happening from each of these planes. Each plane reflects. Okay, we have seen that the diffracted beams will be observed as reflected X-rays if these specularly reflected beams from the set of planes interfere constructively. Okay, so because of constructive interference of this, if the constructive, if this X-rays which has been reflected from various crystallographic planes, if they like interfere or interfere constructively. I hope by now you know what is constructive interference and what is destructive interference. So in that case, we would get some diffraction pattern, okay, due to the interference of various rays which are incident from various crystallographic planes. So there will be many planes, okay. So many planes have not been shown here because of lack of space, but there will be many crystallographic planes, and so there will be many reflected X-rays actually that would eventually form the diffraction pattern. Okay. Okay, so now let's go to some geometry because we really want to find out the condition for diffraction. Okay, so in order to find that, what is the path difference? The path difference is AB minus AD. Okay, for constructive interference, the path difference is AB minus AD. What is the difference between these two paths traveled by traveled by this X-rays? From the difference of the two paths, the difference of the two paths from which the X-rays have been reflected from the two different planes. Okay, these are the two different planes, and what is the difference of their paths? So AB minus AD equal to n lambda, such that n is an integer and it is equal to 1, 2, 3, etc. Okay. Okay, so from the figure AB, so we need to find out AB and AD. Okay, so so sine theta is d over AB. So sine theta d over AB. Where is sine theta? Yeah. Yeah, so this is okay. Maybe I can do some annotation here. So d is the lattice spacing, this distance. So sine theta, sine of theta is this perpendicular d over the hypotenuse AB. Okay. AB. Okay. So what is AB here? Sorry. Okay. AB is d over sin theta. D over sin theta. Okay, AB is d over sin theta, d over, okay, so sorry, sin theta is d over AB, so AB is d over sin theta. Okay. Okay, so now AD, what is AD that we have to find out? Okay, let me stop this annotation now. Uh, okay, where is the mouse? Okay, I'm sorry that this mouse is not responding. Uh, so I don't know why the mouse not responding. Okay, yeah, the mouse seems to be responding now. Okay, so okay, So AB we have calculated. So now we have to calculate AD, because AB minus, okay, AB minus AD. So now how we can calculate AD? Okay. So AD is can be calculated by this triangle ADB. Okay. So ADB is this one. Okay, let me check. Let us check here. So rather than just talking, if I can, and I hope the mouse will not become unresponsive now. So you see ADB triangle. Okay, so this angle is sine twice theta. Okay, because one theta is here, the other theta is here. Okay, so sine twice theta. Can we take sine twice theta? So no, because for sine twice theta we will have this value of dB. So dB by AB. So sine twice theta you cannot take. We have to take AB. So cos twice theta. Yeah, cos twice theta we can take. So let me just write down the value of cos twice theta. Twice theta means theta plus theta. So AD over AB. AD over AB will give you the value of cos twice theta. So what is the value of AD then? We are required to calculate AD. That is AB AB cos twice theta. Okay. Okay, so I hope you have understood how AD equal to AB cos twice theta from this figure. So now I would like to go back to the next slide, which so that we can directly check the calculation. Okay, so I am removing the annotation here, and I would like to go to the next slide. Okay, so AD is AB cos twice theta. So what is the value of AB? AB value we have already. Okay, let me start the annotation again on this because with annotation on, I cannot move between slides. So if I have to move from one slide to another slide, so I have to turn off the annotation and then only I can go to the other slide. Anyway, so AD value is AB cos twice theta. Okay. So what is AB? AB is equal to D over sine theta multiplied by cos twice theta. Okay. So you see AB minus AD is equal to n lambda. So substitute now we have both values of AB and AD with us. So substitute the values here in this equation. Okay. So n lambda equal to AB minus AD. So AB value is here D by sine theta minus AD. AD is AD is D by sine theta multiplied by cos twice theta, because in place of AB the value is substituted from here. Okay. Okay, so AB D by sin theta multiplied by D cos twice theta divided by sin theta. Okay. So from here, from this expression, D by sin theta can be taken common. Okay, take D by sin theta common. So in the bracket will be having 1 minus cos twice theta. Okay. So 1 minus, so D by sin theta is again common here. Okay. And 1 minus cos twice theta from trigonometry it gives us twice sine square theta. Okay, this we get from trigonometry. So twice this sine square theta by sine theta. So sine theta will get cancelled. So there will be 1 sine theta here. So the result which will be available for us will be d twice the sine theta. Okay, so AB minus AD, which is n lambda, and n lambda is in turn equal to twice the sine theta, which we have just calculated from trigonometry. Okay, so this is the Bracks law and how. Okay, I am removing this annotation. So this is Bracks law, and that is how we can derive Bracks law of X-ray diffraction, and this is a very important relation. Okay, so provided you know this you know n, the order of diffraction and wavelength, you can calculate d, interplanar spacing. Of course, you also have to know angle theta. Okay, angle theta you can calculate from your XRD patterns. Okay, X-ray diffraction patterns. And suppose you know theta, d, and n, and in that case you can also calculate lambda. Okay, lambda is the wavelength. So this gives angle theta at which a set of planes of spacing d cooperatively reflect X-rays of wavelength lambda in the nth order. Okay. For monoenergetic radiation mediation used, X-ray photons are monoenergetic, and the equation can be satisfied for particular set of planes having interplanar spacing d provided like this. Okay, so for first order diffraction, so n equal to 1, so here n equal to 1, so theta 1 is written. For second order diffraction, it's n equal to 2, and for third order diffraction, n equal to 3. Okay, so these reflections are known as first, second, and third order reflections. So it will be, you can also write higher orders, fourth order, nth order. Nth order is this one. Okay, and yeah, so that is basically Braggs law. And the angles can theta 1, theta 2, theta 3 for first order, second order, and third order can be calculated like this. Okay, okay, so that's basically, so Debye-Skerrer method we will learn later. So that is a detailed method of determining the various crystallographic planes of a material. Okay. Okay, so reciprocal lattice is another topic which is quite a long topic. So I think I'm not sure we cannot. I'm not finish this in this particular class. So, but okay, let me go to the introductions and some how. Let me go to the introduction part, and then the rest rest of the things we'll learn in the next class. So, reciprocal lattice. So, why it is important? Okay. So, this concept was first developed by someone called Ewald. Okay, Ewald. It's the name of a person. So why it was introduced? So according to Bragg, okay, as per Bragg's law of X-ray diffraction, analysis of X-ray diffraction in terms of slopes of various lattice planes is tedious. Okay, so this was a difficulty. So if we have to analyze this X-ray diffraction pattern in terms of slopes of various planes was a very tough thing. So in order to overcome that, so what was done? So, however, it becomes easier if we, okay, so W is missing here. So, if we consider normal to various sets of planes instead of planes themselves, okay. So, if we can draw normals to various sets of crystallographic planes from a common origin, then analyzing these X-ray diffraction results become easier, okay. So here in this figure, I can tell you quickly what is going on here. So these are various sets of crystallographic planes, and O is a common origin. Okay, so here it is written actually in the description. And again, this much thing I have collected from the textbook I have, Ajay Kumar Saxena, okay, for reference. So O is the origin, and from origin, so you draw this normal, okay. So common normal to each plane. Normal means perpendiculars, okay. And this OR1, the point R1 is chosen in such a way that the OR1 length is equal to some constant of proportionality divided by interplanar spacing. What is the interplanar spacing? The distance between these two crystallographic planes. This shaded plane you can see, and this particular shaded plane you can see. Okay, so this distance R1 is expressed in terms of the reciprocal of the interplanar spacing. Okay, so and this way if you can so R1 represents a set of planes, and similarly we can also represent on this particular normal various sets of other planes. Okay, So about the detailed construction process of reciprocal lattice, we will learn in the next class. Okay. So yeah, here it is also some detailed like description I have taken from the Ajay Kumar Saxena textbook. So we will learn about this in the next class. And these are the reciprocal unit vectors. Okay, so the translation vectors in reciprocal lattice. Okay, and they can be expressed in terms of translation vectors in direct lattice. Okay, so the relationship is something like this. So anyway, I would like to end today's meeting, and thank you all for joining. And in a day or two, I will upload this recorded video to Facebook page of our department also. Okay. So thank you all, and I will continue the topic of reciprocal lattice in the next class. So with this, I would like to end the class. Thank you all.